Okay. So let's quickly look at the scope of what we are covering. We'll be talking about concentration change during the chemical reaction. We'll be talking about equilibrium in dynamic fashion. I'm sure you can see the slide.
Yes, sir.
And then equilibrium constant for aqueous reaction and also equilibrium constant for gaseous reaction, which is your partial pressure. Then Le principle. Then application of equilibrium to Haber process. Let's look at the first part of the slide. Um, from what you are saying, you see that there's a graph there, and the graph is showing the concentration being at maximum concentration of the reactant from the graph, maximum at the top. So the moment the reaction begins, is faster at the start. So the concentrations are full. So there is higher collision frequency, your O-level chemistry, higher collision frequency. It's also in your AS as well. The molecules have higher energy to collide, and they are close together. So there is frequency of collision very fast. So fastest at the start of the reaction, then the moment, and then so the graph, the concentration will be going down. That red line will be going down, down, because the concentration is reducing as time increases. So it slows down as reactants are getting used up until the reactants are fully used up. Well, and while that one is going down, the other line, let's say blue line, you see, will also, is minimal at the start. It will be increasing and increasing until the full product also is formed. So it becomes steeper as the thing is forming and forming and forming. Yeah, so because it's forming, so it's
Right, so it's a little bit difficult to hear you. Sorry.
okay. I should do what?
It's a little bit difficult to hear you.
Okay, okay. Let me look at how to improve the volume then. I will make it I will make it higher, highest volume then, so that you can hear. Mm. So let me make it 100%. Okay. It is now 100%, and I think you should hear better. So as the reaction increases, you have an equilibrium position formed where the two reactants, where the two arrow meets. So I hope it's better now. I hope it's better, not really better.
It's manageable.
Uh, just wait, just better, or else I will take my laptop to go and service it. Okay, but for now, let's manage it because I have to write.
Yeah.
Yes, I have to write in this class. Otherwise, I will use my school laptop. For this,
Oh, it's okay.
yeah, this one is touch screen, so I will be writing. So as the rate of reaction is dependent on the concentration of the reactant, the forward reaction starts off as fast but slow as the reactant are getting used up. So that's about that. I'm sure this slide is very clear to you.
Yeah.
Let me ask you, why is this steeper? Why is this steeper at the beginning for the product?
Because the reaction is fast.
Okay, reaction is fast. So faster reaction is
Yeah.
good. So, but if it's a slow reaction, it will be what? Slopey. That's your
Yeah.
okay. So we'll go on to the next slide. The next slide is still talking. Um, Initially, there is no backward reaction, but as of course, when the reaction starts initially, everything is just reacting. So there is no backward reaction. So, but after a while, you have product forming. Let's see that. But as product form, the speed it speeds up and provided the temperature remains constant, there will come a time when the backward and the forward reaction are equal and opposite. The point here that is talking about here is that reversible reactions, sometimes the forward reaction take precedence until conditions are changed that will favor the backward reaction. So fastest at the start, forward reaction slows down as reaction are getting used up. Then you have backward reaction. As long as you have, the moment you start having more product, then there is tendency for you to have a backward reaction. So an equilibrium reaction will be reached. Okay, so you can see there are several graphs, but there are two major graphs there. The one that talks about product and reactant. Then the other dot and dot is talking about a projection of the reaction itself, normal, the forward reaction, the normal forward reaction, and the normal backward reaction. But when we have about equilibrium between the two of them, so you have the two unbroken lines. Okay, they're a little bit different. All right. So as equilibrium reaction, in an equilibrium reaction, not all the reactants end up as product. That is why you're having the unbroken line. Not all of them will end as product because there is a reversible reaction going on. So in a reversible reaction, let's just say about 50% of the product are formed and you have 50% of the reactant remaining because it is always reversible. It's only when you have irreversible reaction that you have all the reactant being converted to product. But when you have reversible reaction, you can have 100% product. That is what this slide is talking about. So we can move forward there. And also, in reversible reaction, it is never about a single arrow. A single arrow cannot work. And arrows like this, it should be half arrow like this. Even though my slide is also using this kind of arrow, but this is the right one. If you have arrow like this to show that half of the reaction is going forward, half of the reaction is also going backward. This is the one that you should use in your class. It's very, very important about that one. Okay. So let's quickly move forward to the next slide. Okay. Let's look at some important reminder. A reversible chemical reaction is a dynamic process. Why? Because the forward reaction occurs at the same rate as the backward reaction. The forward reaction occurs at the same rate as the backward reaction. Everything may appear stationary, but the reaction is moving in both ways. The position of equilibrium can be varied. Of course, when you change certain conditions, especially temperature, pressure, catalyst, you can change the position of the equilibrium. But we talk about factors affecting equilibrium position. So the position of equilibrium can be changed when you change your temperature, pressure, and the rest. So trying to get up down. Okay, summary. So when a chemical equilibrium is established, both the reactant and the product are present at all times. We're talking about that property of a system at equilibrium. Both the reactant and the product are present at all times. Number two, the equilibrium can be approached from either side. At your A level, most questions we ask if you approach the equilibrium from your left to the right. But when you're in 100 level or when you're in 200 level, you will do both sides. You will start it from product to the reactant like that, and from reactant to product, both sides. But for now, in your ASO, it's just like from reactant to product. They won't pull your leg to product to reactant. No, but it can be approached from both sides, and you have the same answer. All right. The reaction is dynamic. That is, the forward, it is moving forward and backward. That is, the forward reaction is occurring at the same time as the backward reaction. Then the concentration of the reactant will remain constant. So the moment a reaction is at equilibrium, what it means is that the forward reaction and the backward reaction are occurring at the same time. That's what it means. That is why it is in equilibrium. So the word equilibrium is saying that both the forward reaction and backward reaction is occurring at the same time or the same rate. So when they ask you to talk about state two properties of a system at equilibrium. So number one, the forward reaction, the rate of the forward reaction, it is equal to the rate of the backward reaction, or the forward reaction and the backward reaction is occurring at the same time. Then number two, we look at the concentration. The concentration of the reactant and the product remains constant. Once it's at equilibrium at a particular temperature, they are always constant. So those two key parties are very important for equilibrium reaction. Let's look at okay. Let's look at this one. Let's see for an equilibrium reaction of the form A, number of mole A, like that, blah blah. Let's see how we can influence. Okay, let's see how we can talk about the formula there. Okay. Now, in this case, now the constant. Look at to find the equivalent constant Kc. Of course, we knew that one already. Is what the concentration of the product, which is your C times D to the power of their number of moles. So C times D to the power of their number of moles. I'm sure that one too, you know that one already. Over the reactant, which is your A times B to the power of their number of moles. That is your equilibrium constant. And of course, in your AS syllabus, you'll be asked to write equilibrium constant, write the formula. It can be tested on the formula. So by the time the A and the B, the small a and B, have been changed with real numbers, just put those numbers there. You'll also be asked to calculate the formula, the unit of the equilibrium reaction from the formula. That we also do when we do example as well. So Kc is what is Kc? Is the ratio of the concentration of the product over the reactant to the power of their number of moles. So you use this formula to define Kc as the ratio of the concentration of the product to the reactant raised to the power of their respective number of moles. So, and of course, you know that capital bracket represent concentration, and concentration are measured in mole per dm cube. Okay, and so Kc is your equilibrium constant. Let me ask you, what is the symbol for Kp?
The symbol,
Well, how
the Like how am I going to write the expression? Is that what you're asking?
Um, is it going to be, is it like KC as well, or just like, is it how KC is written down, or how do you write your uh,
KP.
KP? And KP, is the P down or up?
What is down?
Are you sure? Okay,
I, hmm.
no problem. We are moving forward. We'll talk about,
Wait, is it
yes,
wait, is it down or up?
for your KP. This is your, let's see, if our case is like this,
Like I know you write partial pressure as P, then the bracket.
KP is not like this.
Oh, okay.
So you're going to have, I think it's like this, capital P. But
Mhm.
I don't think it's K like this. No. Mm. So it's like a capital P. So, but there's a place we'll talk about it. So let's look at this example here. Let's look at this example. Iron 3. What is the color of iron 3?
Um, greenish yellow.
That is the rust, color of rust. Okay.
Oh, okay, brownish,
Rusty brown color. So ion 3 ion is reacting with a NSC minus um, to form this product FeNCS2 minus aqueous. And let's look at the unit for the formula there. Look at the formula there. Very, very important that you get it. Product is your, no, does not have any mole. There's no mole here. So it's just your normal, the concentration like that in bracket per 1. So it's not important. Then ion Fe3 plus to power 1 and NCS minus to power 1. So power 1, you don't write it. So that's very simple. Let's look at the units now. What will be the unit? Overall unit. Yes. Let's look at the overall unit. The one on top is mole per dm cube. Mole
Yeah.
per dm cube. The one below is mole per dm cube squared. So this
Yeah.
one can cancel one. So we have mole per dm cube per minus 1.
Mm-hmm.
So in doing that, we now reverse it. So the dm cube, the per dm cube will be normal dm cube. Then the mole will be minus 1. Because it's to power minus 1. So it's like this over mole per dm cube. So the mole will be MO per 1. dm cube will cancel and become normal dm cube. Do you like, is that okay like that?
Yeah.
So they will test you on units. There is 1 mark on unit. It's very important. So that's about that. All right. So let's look at temperature. The value of Kc now. Kc. Only temperature that can affect the value of Kc, that can change Kc. Kc is not the same as position of equilibrium. Position of equilibrium is affected by temperature, pressure, concentration, catalyst. But that is position of the equilibrium is affected by all of those factors. But the value of Kc, equilibrium concentration, that constant, can only be affected by temperature. So equilibrium constant remain constant at a particular temperature. and changes when that temperature either increases or decreases. So the only factor that affects KC is temperature, and pressure, catalyst, and all of that do not affect the value of KC. They can only affect the position of equilibrium. The Chatelias principle, they hardly ask people, but they can also ask anything. Since it's in your syllabus, they can ask you. So when a change is applied to a system in dynamic equilibrium, the system reacts in such a way to oppose the effect of the change. There's a simplified way to do that. So simplified way to do that. But this is very simple. When a change is applied to a system in dynamic equilibrium, look at the word dynamic equilibrium. The system reacts in such a way to oppose the effect of that change. Okay, so this principle is key to our success in this topic. We are going to be using it a lot. Okay, that's about that. Let's move on. Let's look at the first one, concentration. Concentration. Okay, let me first ask you, what is concentration?
Concentration is the amount of mole per dm cube.
Okay, amount of substance dissolved in a certain amount of solution.
Okay.
So that is not, it's just for you to know that concentration. What is the formula for concentration?
It is amount over volume, I think.
Number of mole over volume. Concentration is number of mole over volume, or
1,000 times. Oh, oops.
your number of mole over over volume is this is
times 1,000, yeah, over volume.
Yeah. So anyone, but this is for the matured mind. The amount of substances in a particular volume of water or solution. So amount of substance over, okay, dissolved in a particular volume of a solution. That is that. So with this one, you can always define it. With this formula, you can always define it. It's easier for you to define. Okay, so now when you increase the let me go with the slide. The equilibrium constant is not affected by the change in concentration at constant temperature. All right. To maintain the constant, the composition of the equilibrium mixture changes. That's where we apply the Chatelias principle to ensure that the KC remain the same. The concentration of the mixture will change, that KC remain the same at constant temperature. So if you increase concentration of a substance, the value of KC will theoretically be affected. That is, if you increase the concentration, value of KC will theoretically be affected, but later it will remain the same. So as it must remain constant at the room temperature, the concentration of the other species change to keep it constant. That is also important. Let's look at the next slide. Let's look at an example of a popular. This esterification reaction is very popular for equilibrium concentration because it is 1 mole each. And for AS level, they will not go to things like complex reaction that involve maybe 3 moles, 4 moles, like that. So they give a simple reaction of a esterification reaction that reactant and product are one mole each. So they are common question. This area of talking about a substitution reaction. So we have ethanol reacting with ethanoic acid to give us ethyl ethanoate. So this is ethyl ethanoate plus water. So reversible arrow. And so the Kc will be the product over the reactant, all raised to power of the mole of mole with 1. Then over the reactant, we have the reactant as well. Okay, and Kc is equal to 4. Kc has been given to us as 4 at 298 Kelvin, increasing the concentration of ethanol. The first thing, this will make the bottom line, larger. This one will be larger because you have increased this one. So the amount of mole of that will be higher. So Kc will be smaller. That is correct. To keep it constant, this one will react together. The two of them will react together. So this will reduce the value of at the bottom line and increase the one at the top. Eventually, the value will become constant, or the constant will be restored. So when you increase the concentration of the reactant, the position of equilibrium will move forward because the reactant will react together because they are more than the product, will react together and then form more of the product to restore the value of Kc to make it constant back to 4. So increase in concentration of reactant, the position of equilibrium move to the right-hand side. Okay, is direct. The same thing happens when you increase the concentration of the product. The position of equilibrium will move backward. Okay. So decreasing the concentration of water. When you remove water, when you remove, they normally ask you that if water is removed and water is a product, it means that there will be lesser concentration of water of the overall product in terms of concentration reduces. And once it reduces, it will make the reactant to react and produce more product. So when you remove part of the product, equilibrium position shifts to the right-hand side. So you must get that one very clear. Part of the product, once it has been removed, forward reaction will be initiated to replace them back. So position of equilibrium moves forward. So it will make the top liner smaller, and that means that some of the reactant will react to replace the water. So equilibrium position shift to the right-hand side. Any question from there?
No, sir.
Okay. All right. So let's quickly talk about the summary of the whole thing. Increase in concentration of the reactant. Equilibrium moves to the right-hand side. Decrease in concentration of a reactant. Equilibrium moves to the left-hand side. When you decrease it, so the product will react to replace what you have removed to restore it back. Then increase in concentration of the product. Of course, there are more products and there will be lesser reactant. So to move to the left-hand side, very easy. Decrease in concentration of the product, we move to the right-hand side. Okay, so let's look at that. SO2 plus O2 to give you 2SO3. Okay, to get the effect of increasing the concentration of oxygen. Of course, when you increase oxygen, if you move to the right-hand side, because there are more reactant than product, so if you move to the reactant to restore. What happens to if you decrease the concentration of SO3, it will move to the right-hand side? Very good. Now, let me bring in some additional stuff that you must know. Look at this reaction, Cr2O7 plus water, that Cr2O7 plus water, reversible arrow to give me Cr O4 2 minus plus H plus 2 here, then 2 here. No. Okay. 2Cl, 8 oxygen, then 2 moles of water. Okay, 8 oxygen. Okay. Yeah. Look at this reaction. This is orange in color. Orange in color, and this is yellow in color. Okay. So these are aqueous reaction, aqueous. They're all aqueous, except water is liquid, of course. The rest are all aqueous. Now, let me going to ask you, we are bringing in color to the question now. The one we have been doing, these ones are all colorless. Now you're bringing color. If I increase the concentration of Cr2O7, what will be the effect? Yes.
It will become more yellow, more orange, sorry.
If I increase the concentration of Cr2O7,
Or do you mean are you talking about the equilibrium? Where would it
what will
shift?
be the effect now? Yeah, that is about what I mean. Yeah.
Oh, I'm sorry. It will shift to the right.
Okay. So what do you observe?
That when you increase Cr2O7,
Okay.
yeah.
Okay, I understand. I can understand now. So now this is what happens in your AS chemistry. Once they add color, they want you to comment on the color change. So you already know that increase in concentration of the reactant, it is going to be forward reaction. So your first answer is that the position of equilibrium shifts to the right hand side. More of CrO4 2 minus will produce. That is the meaning. Since it is shifting to the right hand side, more of CrO4 2 minus will be produced, and then the orange color of Cr2O7 will fade because it will react with water. So orange color of Cr2O7 will fade, or the reactant mixture will fade, and then you will see the yellow color becoming intense. So we can summarize what are the likely answer. So the first answer that you're going to have will look like something like this. Number one, position of equilibrium. Shift, the word shift is very important. Shift to the right hand side. If they want to punish students, they will say that is 1 mark. They will put 1 mark there that for strength is shift. Then they will not say somebody. Number two, they will not look for candidate that will write on the color changes. They will not say either orange color of Cr2O7 2 minus fades slash, for example, yellow color of Cr O4. becomes intense yellow. Intense yellow. Yellow color will become much more yellow because there are more, because since the position of equilibrium has moved forward, you will have more of yellow color than orange. The orange is fading away, yellow color is fading away. They will associate that one is also 1 mark. They will now again tell you that what there'll be more of CrO7 2 minus at equilibrium than that other one. So they will tell you more CrO4 2 minus produced to restore the equilibrium. So the two major ones are the first two: position of equilibrium shift, or the color changes, orange color fade, yellow color become intense, or simply orange color. The two of them will be 1 mark. Anyone you're right. Okay. Then more CrO4 2 minus is produced. That is about that one. They will now ask you, state what could mention one reagent that could be used to initiate the backward reaction. State a reagent that you can use to initiate the backward reaction. You look very well at the product. Look very well at the product. What is the easiest reagent to use if you don't use CrO4 2 minus? Yes.
KMNO4.
Use what?
So don't worry.
Okay, good. So we are learning gradually. Look at this one. Look at this one. What does it represent? H plus. What does
Oh,
it
okay. Like water or something.
represent? What?
Like an aqueous solution.
H plus now. H plus represent acid. That is acid. See that?
Oh, okay.
Mhm.
Oh,
So,
okay. Makes
so,
sense.
so when they want to bring in H plus question like this, they will tell you. So H plus. So add more hydrochloric acid. Add more sulfuric acid. So the moment you increase, so they want you to know that H plus represent acid. Even in your you should do acid base equilibrium. So H plus represent acid. So add extra acid. The moment you add acid into it, the concentration of H plus will increase because the acid you are adding, either HCl or folic acid, the overall effect, what if you add like HCl, Cl does not have any role to play because it is not in the product, it is not in the reactant. So what matters most there is the H plus. So the H plus is in product. So it will increase the concentration of the product. That will initiate a backward reaction. So they will also ask you that if HCl is added, in case they're asking, suggest. That is one part of the question. If they ask you, if they answer, okay, a student decided to add HCl to the reaction mixture, state the effect of the HCl. Of course, you must also know that the HCl supplies hydrogen ion concentration, which increases the overall concentration of the H plus in the reaction mixture. So the overall product increases now. So that will make the CrO4 2 minus plus H plus to react to produce water and Cr2O7. The meaning is that, so let's write the possible answer now. The possible answer will be equilibrium position will shift to the back, I mean to the left-hand side. That'll be 1 mark. So so let's start now.
Now, oh yeah, to the left.
Come again.
You said to the left.
The what?
The equilibrium position is shift to the left.
Left, yes, thank you. Yes, correct. So the possible answer will now be in this manner. Number one, equilibrium position shift to the left-hand side, 1 mark. Then, since the H plus we react with Cr2O7, the concentration of, since the H plus will react with CrO42 minus, the concentration of CrO42 minus will decrease, meaning that the color, the yellow color, will fade. So the second mark will be yellow color of CrO42 minus fades slash
The orange color becomes more intense.
Cr2O72 minus color becomes intense orange. The orange color becomes much more intense. Or you can simply say that the reaction mixture, the orange color, the color of the reaction mixture becomes more orange. That summarizes the whole thing together. But technically, yellow color will fade and orange color becomes more orange or become much more intense. Then, since CrO42 minus is reacting with H plus, there will be higher concentration of Cr2O7. That is why the color will become much more intense. So that is that one. So you look at it like that. Now, they will not go ahead and test you because your AS is always applied. Now, let us now look at this one. From what I've done for you now, adding HCl to include H plus. What can you, okay, I will now ask you this following question. I will ask you, what suggest a reagent that can be used to initiate a forward reaction? Suggest outside the use of water and Cr2O72 minus. Yes. Suggest a reagent that can be used to initiate a backward reaction. I mean a forward reaction. What will you say? Yeah.
Will it be a base?
Okay. You think about, I have used here, I use HCl, have you?
Yeah.
So if HCl can move backward, then the opposite of HCl should move it forward. And that will be what? Because this is an acid. So what is the
Yeah,
opposite of an acid?
a base.
So a name base. Now give me a base.
Oh, okay, I should name a base.
Yeah.
Okay, okay. Just any base.
Any base that is alkali, an alkali.
Oh, okay, like KCl.
K what?
KCl.
Is that a base?
No, that's not a base, sorry. Um, KOH.
KOH. Good. So your KOH or NaOH or LiOH or BOH bracket is an alkaline. These are alkali. They are soluble bases. So any of them. So if this one now, KOH will give, or any of them will give you OH minus plus K. The K here has no any effect. What has effect is OH. The OH will not react with water. It will not react with Cr2O7 2 minus. It will not react with CrO. It will react with what? H plus. So the OH react with H plus to form what? Water. So it will react with H plus and remove the product and decrease the concentration of the product. So if equilibrium position moves forward, see that? So color change in equilibrium can be what they can ask you in your also AS. Because so that's about that. They can either remove it or ask you to suggest a reagent. But in most cases, it can happen in your A2. It can happen in your A2. But we do not know when such can be repeated. We'll check a question after now. You will see some things that we are talking about right now. So the moment you add OH, KOH or NOH, it supplies OH minus that will react with H plus. Why? Because it requires lower activation energy. Why? Why am I saying lower? This is minus and this is plus. They are opposite charges. The rest, OH minus, will not go and meet OH, will not go and meet 2 minus because they have the same charges. So they will repel. They will have higher activation energy. So no reaction. Then OH minus will not go and react with CrO for 2 minus. The same charges. It will repel. Water has no charge. Even though it has partial, it's polar. It won't go and meet, it won't go and meet that one. The easiest one is the one of H plus, which is opposite. So once it reacts with that, it has decreased the concentration of the product. Then it moves the position of the equilibrium forward. They will not ask you state the effect of adding. If they ask you to suggest and explain the effect. So, or they give you they say a student added potassium hydroxide to the solution. What will be the effect? If they want to make it simpler, they will tell you, tick the correct answer. No effect. It will produce effect. So they will give you, what do you say?
Oh yeah, don't worry.
Okay, so they will give you all these options. I have to tick one. So if position of equilibrium will move forward because the OH will react with the H plus. So I'm giving you deeper equilibrium for you have it, so deeper equilibrium. Then, so if it goes forward, it means that the orange color of Cl2O7 will fade and yellow color becomes intense, or simply the reaction mixture will become yellow in color overall. Is that clear like that? Is that clear? Are you still there? Are you still there?